Good morning, guys. I'm going to switch here to see if this is actually recording or not. I don't know if it is. We will see. Sorry I couldn't be in class today. I'm home with Caden, who isn't feeling well. But if we were in class, this is what we would be doing. So I thought I would try this program out and see if it actually will work. Last class we talked about combinations, which was adding, subtracting, multiplying, and dividing functions to each other. Today we would be taking that composition component of last class's lesson and using it to apply to inverse functions. So inverse functions are two functions that are opposite of each other, which means whatever we would do in one function, we needed to be doing the exact opposite in the other function in order for them to be inverses. So today we're going to look at some rules that will allow us to determine if two given functions are inverses. Then we're going to go through a process and actually, if we're given an f function or a g function or given one function, go through a process to find what that inverse is and then use our rules of compositions to prove that what we found is in fact correct. It's like your check mechanism. Like when we solve an equation, you take your value of x, plug it back into the original equation, and follow our order of operations to make sure it works. Our composition process is the way that we prove the inverse we found is correct. So by rule, two separate functions are inverses if their compositions equal x. If you remember from last week, Monday, this composition, this is what a composition looks like. It takes one function and evaluates it with the expression of the other function. Same thing here. Our function of g is evaluated with the expression that represents the f function. So in order for us to determine that two functions are inverses, we have to form compositions, work them out, and both of them have to simplify down to a positive x. So here's an example of that. We're given an f of x function and a g of x function. The f of x function equals 6x. The g of x function equals x over 6. So to determine, as they're asking, if these two functions are inverses, we're going to form the compositions. Both of them. Okay. So this one says we start with our f function. And in our f function, wherever there's an x, we're going to plug in our g of x function. And we're going to work out this problem. This is a multiplication problem of fractions. Remember, 6 is the same thing as 6 over 1. If we multiply fractions, we can multiply the top, we get 6x, multiply the bottom, and we get 6. 6x over 6, those 6's cancel out, and it leaves us with x, which is what we want. So then we check the next one. Here they want us to start with the g function, which is x over 6. And inside that g function, where there's an x, we replace it with the f of x function. We get 6x over 6. We already know those 6's cancel, and it leaves us with x. So since both compositions simplify down to a positive x, we are able to say that f of x and g of x are inverses. Let's look at another one. Again, we're given f of x and g of x. In this example, 5x minus 9 is our expression for f of x, and g of x, x plus 5, is being divided by 9. So if we think about the word inverse, it means the opposite. So if we look at this f of x function, over here, my x is being multiplied by 5, and then I'm subtracting 9 from it. So inverse ways, if g of x is an inverse, wouldn't I have to be dividing by 5 since over here I'm multiplying by 5? Well, here I'm dividing by 9. So we're going to make a preliminary assumption that f of x and g of x are not inverses, which means if they're not, their compositions should not equal x. So my first composition says I'm going to start with f, and inside f, I'm going to plug in the expression that represents my g of x. Now in this expression, they want me to multiply 5 times the rational expression and then subtract 9. Remember, 5 is also 5 over 1. So 5 needs to be multiplied by x plus 5, which gives me 5x plus 25. And my denominators need to multiply, and that gives me 9. So that expression is subtracting 9. Remember, 9 is the same thing as 9 over 1. If I'm going to subtract these two fractions, then don't they have to have the same denominator? So I'm going to change 9 over 1 to a fraction with a denominator of 9, which means 1 multiplied by 9 to get 9, so 9 needs to multiply by 9, which gives me the fraction of 81 over 9. Now, since they have the same denominator, I can combine the expressions in the top. So 5x plus 25 minus 81, let's see, what does that give us? Let's look, see if I can find my math tools here. I know I have them, I just don't know where they are. There they are. The calculator. So 25 needs to subtract 81. That gives me negative 56. So I have 5x minus 56 over 9 is my simplified expression for the composition of f with g of x. That does not equal x, so we can already determine that f of x and g of x are not inverses. Okay, now for me, that's enough. You wouldn't have to do the composition of g with f of x. MyMathLab is going to make you do both of them and then make your decision whether they're inverses or not. So we'll go through this one quickly. G of x is x plus 5 over 9. Remember, in your g of x, they want you to evaluate with the f of x function of 5x minus 9. We simplify that. We get 5x minus 4 over 9, because minus 9 plus 5 gives us negative 4. That can't simplify anymore. Again, it doesn't equal x, so it enforces that f of x and g of x are not inverses. Okay, let's look at one last one here. This one includes a radical and a squared term. Again, we know that the opposite of squaring something is to take the square root, so it's a possibility that these are inverses. The only way to prove it, you got it, is to form our compositions. So we're going to start with f of x, which is x minus 1 under the radical. And wherever there's an x, we're going to plug in the g of x function of x squared plus 1. We simplify that under the radical. X squared plus 1 minus 1, those cancel, so I'm left with the square root of x squared. The square root of x squared is x. So since that one checks out, we do have to, in fact, do the second composition. So now we're going to start with g of x. Inside g of x, I'm going to plug in the square root of x minus 1, which is my f of x function. What happens when we square a radical? It makes that radical disappear. So we're left with x minus 1 plus 1, which again leaves us with x. So that work proves that, I'll write it backwards, g of x and f of x are inverses. Okay, so the rule here, form compositions. We did that in the last section. So all we have to do is take the two functions, check their compositions. If both expressions or both compositions simplify down to positive x, then we can say they are inverses. If one of them does not or both of them do not, then they are not inverses. Okay? So the second thing we're going to do in this section is actually find the inverse of a given function. So if we're given the function of f of x, then the notation for its inverse looks like this. Now the reason why it looks like that is because my original function has an exponent of 1. The opposite of positive 1 is negative 1. If this is our function right here, f of x, and our inverse is f inverse of x that looks like this, then again, this is the same rule. The only difference is that I am calling my second function, instead of g of x, I'm calling it f inverse of x. So it's the same rule. Two functions are inverses if their compositions equal x. The notation is different. If my first function is f of x, and now if I have to find my inverse, I'm going to label that second function that I find using this notation to tell somebody this expression is representing the inverse of my original function f of x. Okay? How do we find that inverse? Well, there's a lot of background rules that go into this. I'm going to go through a lot of examples, but the same process applies. This is the step-by-step process to find an inverse of any function. First, we're going to take the f of x function notation out and put the y back in. We talked about that in the first section. The f of x and y are the same thing. If there's a y in there, then it's now an equation. If an f of x is in there, it's a function. So we're going to take the function notation out and replace it with the y. Then we are going to switch places of the x variable and the y variable. We are literally going to pick up the x and the y and switch them. Nothing else changes. Nothing that's attached to the x goes with it. Nothing that's attached to the y goes with it. We are simply going to pick up the x and the y and switch them. And then we are going to solve that equation for y. And here's where the hard part comes in, because you have to remember how to rearrange using inverse operations and equations so that y becomes by itself. Once we get an expression for y, we're going to take that y out and replace it with inverse notation. So we are going to say if y equals this expression, then that means this expression is the inverse of our f of x function. Lastly, we are going to prove it. We are going to form the two compositions. Our inverse function is going to get plugged into our f, and it has to equal x. And then we're going to start with that inverse expression we just found, plug in our original function into it. Again, that has to equal x. Okay, so this is what that looks like. We're going to start with a pretty simple one. Okay, step one, f of x becomes y. Step two, x and y switch places. And step three, I have to solve for y. So to solve for y in this case, I'm adding 5, so the inverse of addition to 5 is to subtract it. So x minus 5 equals y. If we switch places, that means y equals x minus 5. Fourth step, that y comes out and inverse notation goes in. This is what you're trying to prove. Okay, this is what we found. We found that if f of x is x plus 5, then my inverse of that f of x is x minus 5. Okay, that's steps 1 through 4. This gives us our inverse. Now we need to prove it. The proving part is what we just did in the last 3 examples. However, we're just using different notation. Prove that the f you're starting with and that inverse expression you just found are inverses, because if they are, their compositions will equal x. So we're going to start with x plus 5. We're going to plug in the inverse expression of x minus 5. X minus 5 plus 5, those cancel, leaves me with x. Do the opposite composition. Now start with your function that your inverse you just found and plug in the original function. So our inverse we found was x minus 5. We're going to plug in x plus 5. X plus 5 minus 5, those cancel, leaves me with x. This, and this are the 3 answers you should be looking for. Go through the process to find your inverse. Prove that inverse by checking the compositions, both simplify down to x. Okay. Here's another example. This is a cubic function. Okay, step 1, f of x gets replaced with y. Step 2, x and y switch places. So now x equals y cubed minus 1. Step 3, solve that equation for y. So here's my y term, so I need to add 1 first. So x plus 1 equals y cubed. Now we haven't done a y cubed one yet. However, We know that the opposite of squaring something is the square root, so the opposite of cubing something is the cube root. The cube root of y cubed is y. Rules of equations, whatever I do to one side, I have to do to the entire other side. So I'm going to take the cube root of x plus 1. So y equals the cube root of x plus 1. That means in the fourth step, we are proving that the inverse function of f is the expression, the cube root of x plus 1. Here's what we think our inverse is. We need to prove that or check our answer, make sure it's right. We know we can check it by plugging it into a composition. So we're going to start with the first one. The first composition, you start with your original function given, and inside that function, you plug in your inverse, which we found to be the cube root of x plus 1. If squaring a square root eliminates the root, then cubing a cube root will eliminate that root. That leaves me with x plus 1 minus 1, which equals lovely little x, which is what we want. Form the second composition. Now we start with the inverse that we found, which is right here, and plug in our original given function. So we're starting with the cube root of x plus 1. Under that cube root where there's an x, I'm replacing it with the original function of x cubed minus 1. X cubed minus 1 plus 1, that plus 1 minus 1 will cancel, so I'm left with the cube root of x cubed, which if the square root of x squared is x, the cube root of x cubed is x. Exactly what we wanted. This and this prove that this is in fact correct. Okay? One more. This one is going to be a little bit more difficult because your x is now in the denominator position. We have only worked with x being in the numerator. So usually we're used to saying x is being divided by 4. So x is what's being manipulated. It's being divided by 4, so I know the inverse would be to multiply by 4. This is a little bit different because 4 is what's being manipulated by x. It changes the way it looks a little bit. However, the process doesn't change. First step, f of x becomes y. Second step, x and y switch. Third step, solve that equation for y. Okay? Watch closely. Here's our y term. Ignore where that y is right now. I'm adding 9 to the y term, so I need to subtract 9 first. So x minus 9 equals 4 divided by y. Now the rule of fractions is no matter where your variable is, if you're solving for a variable that's inside a fraction, you need to get rid of that fraction. We've talked about this many times this year. The only way to get rid of a fraction is to multiply by the denominator. If I multiply 4 over y times y, that cancels, leaves me with 4. On the other side, the entire expression of x minus 9 has to multiply by y. Now, your first thought is to distribute that y. We don't actually want to go through that multiplication process because if I do that, then I'm going to have a y in 2 terms, and that makes it even more difficult. I'm not going to distribute this. Instead, I'm going to say if y is being multiplied by x minus 9, the opposite of multiplying by x minus 9 is to divide by x minus 9. Cancels that factor and that factor out. The other side has to be multiplied by x minus 9. So I get the expression y equals 4 divided by the binomial x minus 9. Which then means in step 4 that y comes out, the inverse function notation goes in, so the inverse of f of x is the expression 4 divided by x minus 9. Now again, you guessed it, we have to prove it. So, people often skip this step. MyMathLab will not force you to do this step. I will force you to do it, so get used to doing it, okay? To me, this is the most important step. It's what proves you're right. Don't you want to know you're right? I want to know I'm right. I kind of look at this as when people say, well, why do I have to prove it if I know it's right? Well, it's like me going to the bank and say, give me $1 million. They're going to say, prove to me you have it, which I don't. But, okay, the proof is something that we do in everyday life. It's something we have to get used to doing in math as well. So form your composition. Start with F. Plug in your inverse expression into F. So we have 4 over x plus 9. This one's going to get a little messy and yucky. X is 4 over x minus 9. That's my inverse. This looks weird. We are not used to that. This says 4 is being divided by the fraction of 4 over x minus 9. This and this are equivalent. I just wrote it differently. Now, we already talked about, and we've worked with it many times, when you divide fractions, you change that to multiplication by the reciprocal. Don't tell me you don't know how to do that. You do. Which means now 4, which again is 4 over 1, is being multiplied by x minus 9 over 4. Look at that. That denominator cross cancels. I'm left with x minus 9 plus 9. Those cancel. We get x. A lot of work, but it proves we are on the right track. That's the first composition. Now we need to do the second. We're starting with our inverse and plugging in our original function. So our inverse is here, 4 over x minus 9. Inside that x, we're going to plug in 4 over x plus 9, which was our f function. Okay? So if we look at this denominator, plus 9 minus 9, doesn't that cancel there? So we're left with 4 divided by 4 over x, which looks like this, 4 divided by 4 over x, which means we need to change that to 4 times x over 4. Change your whole number to a fraction if that makes it easier. You can cross cancel your 4's and you're left with x. Okay? There you have it. There's plenty of other examples that we can go through, but a majority of them are similar to these. Make sure you follow the process. Okay, nice thing about this video is you can stop it, replay it, look at it, excuse me, as many times as you want. Okay, last thing in this chapter is what we call the horizontal line test. In section 1, we talked about the vertical line test. Remember, vertical lines go up and down. Okay, this is a vertical line, right? This is vertical. This is horizontal. Okay. The vertical line test will tell us if the graph is in fact the graph of a function or not. So if we look at all of these, A, B, C, and D, all of them would pass the vertical line test. Let me get that line if it'll let me. This linear equation is a linear function. This quadratic parabola is a function. This is a trigonometric function. It has peaks and valleys, but it still passes the vertical line test. This is a cubic function. It will also pass the vertical line test. Okay. The horizontal line test will tell us if a function has an inverse or not. Not all functions have an inverse. Okay. If a horizontal line can be drawn through your function, and at every single point it'll intersect the horizontal line once and only once, then it will have a function. When they say that, they say, is this function one-to-one? So this linear function is one-to-one, which means its one function has one inverse. You will hear and see that vocab one-to-one. This linear function passes the horizontal line test, so it will have a function. This quadratic function, as you can see, fails the horizontal line test. This quadratic function is not one-to-one, which means it doesn't have an inverse. So you'll never be asked to find an inverse of a quadratic function because there isn't one. Okay. Same thing with this trigonometric function. It fails the horizontal line test, so it is a function, but it doesn't have an inverse. This cubic function passes the horizontal line test, which is why we can find an inverse of this function. We just did it in this example right here. Okay? As always, if you have any questions, please ask. I am home today, but you can email me. Homework for this is on my math lab. It will be due the next class. See you guys soon.